situation we have is following. So we have a tank. And with tank we have two pipes. From the first pipe, say, let's call this pipe capital A. We have fluid is pouring in to tank, and through the second pipe, B, it's pouring out. Okay. And the tank has some solution inside of it, some fluid. Okay, so that's the situation. Now let's provide a little bit more information into it. So from A, we have brine solution is coming into a tank. Brine solution. Okay. And it's coming to trade at a particular rate and a particular concentration. Two numbers. Okay. Through pipe B, we have that brine is leaving. So brine is leaving. Okay. And the concentration of brine depends on the concentration of salt, I guess, in a tank. So we'll assume that solution is well mixed. Okay. Brine is coming to trade. Let's put like letter A here. Okay, we'll use A. And say liters per minute. Leaving a trade, I will put B. Liters per minute again, same units. Let's make it easy firstly. Let's let V be the same rate at which it's coming at the same at which it's leaving. So A, same letter A. Okay. And concentration, let's put like I'm not sure, A0. A0. Okay. It's a percentage. Actually, I would make it as a decimal. Let's put as a decimal. This will be easy for us to write if we put it as a decimal. Concentration A0 in decimals. Okay. So the question is determine how much salt is in the tank at time t. I'm going to use letter, I guess, X. That would stand for amount of salt in a tank. Okay. So let's X stands for amount of salt in a tank. Okay. Let's see. I will use letter S, C, for amount in liters. Liters of brine in the tank. So C is not changing because we have as much brine coming in, and same amount as leaving at the same rate. So volume over brine of a solution in the tanks stays constant, right? Because of that, because we have the same rate here and here, same rate. And I guess I will measure concentration in, let's say, kilograms per liter. Kilograms per liter. Then amount of salt in the tank will be measured in kilograms. Okay. Now let's set up our differential equations. Set up differential equation. So what we have is we have amount of salt in the tank is changing. So X with respect to T is changing. I guess I need to say what T is. T is time in minutes. Okay. So amount of salt is changing with respect to time. So dx dt equals. So we have salt which is coming, and we have amount of salt which is leaving, right? So coming through pipe A and leaving through pipe B. So let's figure out how much salt we have coming. So through pipe A, how much in? So that's more or less straightforward. All that we have to do is just take how much volume, it's 8 liters per minute, and multiply it by concentration, is 0. So that's how much salt is coming in. So salt in. Okay, now let's figure out how much out. Out through pipe B, so out through pipe B, out through pipe B, so salt out. So we have A, and we need to multiply A by concentration. To figure out the concentration, what we do is we know how much salt we have in the tank. It's X. And we know how much volume, how much that brine we have in the tank. It's C liters. So to find the concentration, we take X and divide by C, right? To find concentration, you take X, divide by C. So how much is per 1 liter? So you take X and you divide by how much is the volume. Okay, so it's concentration, that is concentration. So amount of salt divided by volume. So we have X, at the moment we have X kilograms of salt in a tank, and we have C liters in a tank. So concentration is X over C, and we multiply it by A because that's how many liters of solution is leaving the tank. Okay, so we can know what is in. We know what is out. Okay. We add in, we subtract out, and we have our expression. So for in, it's A times A0 minus, because it's out, it's A times X divided by C. That is how we differential equation. And it will be really easy to solve it. All that we have to do is just separate variables, right? Easy to solve. By separating variables. For example, separating variables. You also can notice that you also can solve it maybe by linear, by finding integrating factor. So whatever is easiest for you. Okay. So that's in general setup. And now let's set up the problem with numbers and see if that will be easier or harder. Okay. So Brian is coming trade liters per minute, leaving at the same rate. Okay. And here a concentration at which it's coming. Kilograms per liter. So let's pick numbers. Do 50, right? Because 1 liter of water is basically 1 kilogram of water, right? And it's difficult to imagine that 1 kilogram of water you will be able to solve as much water as as salt as 1 to 1. So 50 grams. Okay. So we also need to know initial amount of salt in the tank. Okay. We might assume that we started with pure water in tank, or we might assume that already has some salt in it. So do you want to start with pure water or not? So 0, pure water. And then let's see, we also need to know how much pure water is in the tank. So initially, there was liters of pure water. So because I'm saying that. Okay. Now let's set up our problem with numbers. So I'm going to put using X for amount of salt in grams, I guess. T for time in minutes, starting from some point. Then we have dx dt equals. We have 10 liters coming in and concentration 50 grams per liter. So we have total 10 times 50, which is coming. Minus, we also have 10 liters leaving, and concentration is, we take X and we divide it by 100. Are we good with differential equation? And also, if you like, that's IVP. But IVP has initial condition that X of 0 equals to 0, because initially we had a pure water, right? So X of 0 equals to 0. So that's IVP. So that's for IVP to solve. So IVP. And that's supposed to be more or less straightforward, because again, we have dx dt equals 500 minus 0.1x. Split them. Dx divided by 500 minus 0.1x equals to t dt. Natural log of 500 minus 0.1x equals to, I'm saying t dt, I'm already thinking about 1 dt, right? T, c. And the coefficient here, because I'm doing substitution, my best guess it will be -10, something like that. So now get rid of natural log. So we're going to get that expression here, right, will be positive. It's kind of obvious because initial concentration is x equals to 0. So it will be positive. So I can ignore that absolute value. If you want, right from beginning. If you like, keep it and then use initial condition to take care of it. Somehow it will be taken care of. Anyhow, we're going to get ln of 500 minus 0.1x equals t over -10 plus constant again, because c over -10 is constant. So 500 minus 0.1x. Now to get rid of ln, take e to r. Rewrite as e to t -10 times e to the c. So 0.1x equals to 500 minus e to the c is a constant. I'm going to write k for it. E to -t over 10. And I guess multiply by, divide by 0.1. So x equals 5,000. K times 0.1. K divided by 0.1 is again constant. So constant e to -t. Now I want to look at the problem and figure out, whenever that solution will make sense or not. So how you can look at that. So if you just look at the problem, right, then you kind of see immediately that eventually, right, after a long time, which I mean when t is approaching infinity, right, concentration in the tank will be 50 grams per liter. Does it mean eventually, again, when t is approaching infinity, we're going to see 50 times 100, which is 5,000 grams, right? So when t is approaching infinity, we should expect there will be 5 kilograms of salt in the tank. Okay, that's what our intuition tells us. Now let's see if the formula will tell the same thing. So let's look at the formula. When t is approaching infinity, e to the -t over 10, we're going to get e to the -infinity, which is 0. So we'll get when t is approaching infinity, x will be approaching 5,000 grams. So let's agree with what we said. Okay, so at least in that sense, our answer makes sense. Okay. So what you often want to do is at the end, to get your answers, try to figure out the number that makes sense. Maybe even you set up mathematical model, maybe it make no sense from a physical point of view. Now recall that we are actually doing a IVP. So recall the initial condition. X of 0 equals to 0. We started with a pure order. So we have 0 equals to 5,000 minus k. Each with 0 is 1. So we get k equals to 5,000. So we're going to get, as a final answer, we're going to get x equals to 5,000 minus 5,000 e to negative t over 10. And maybe it will be better if it factor 5,000 out. Okay. The final answer maybe that.